There is a moon in our solar system that is actively spraying its own ocean into space. Right now, as you read this, as you go about your day, a small icy world orbiting Saturn is firing jets of liquid water from cracks in its southern pole at speeds exceeding 2,000 kilometers per hour. These jets carry material from a global liquid ocean hidden beneath the moon's frozen surface. They carry salt, they carry organic molecules, they carry hydrogen, produced by chemical reactions between liquid water and hot rock on the ocean floor. And in October of 2025, fresh analysis of data collected by NASA's Cassini spacecraft revealed that those jets also carry something that stopped scientists in their tracks: complex organic molecules, freshly synthesized in the ocean below, that had never been detected in the plumes before. The co-author of the study, ESA Cassini project scientist Nicholas Altobelli, said it was fantastic to see new discoveries emerging from Cassini data, almost 2 decades after it was collected. The lead author of the study pointed out that these molecules prove the complex organisms are not just a product of long exposure to space, but are, in his words, readily available in Enceladus's ocean. An ocean, beneath ice, in our own solar system, that is actively producing complex organic chemistry and spraying it into space for any passing spacecraft to sample. And if something lives in that ocean, we may already have flown through it without knowing. This is not a distant planet around a distant star. This is Saturn, a world our own telescopes have been watching for centuries. A moon we sent a spacecraft to visit. The discovery that Enceladus contains a global subsurface ocean, confirmed in 2005 when Cassini first detected the plumes, was one of the most significant findings in the history of planetary science. It demonstrated something that fundamentally changed how astrobiologists think about where in the universe life might exist. Life does not require a planet in a habitable zone around a star, with the right surface temperature for liquid water and a thick enough atmosphere to maintain it. Life requires liquid water, energy, and chemistry. All three exist beneath the ice of Enceladus. The ocean is kept liquid by tidal heating, the gravitational flexing of the moon's interior, as Saturn's immense gravity squeezes and stretches it continuously. The energy comes from hydrothermal vents on the ocean floor, confirmed by the presence of molecular hydrogen in the plumes, which is produced when water reacts with hot rock, and exactly the process that drives life at Earth's deep ocean vents. And the chemistry, confirmed by the October 2025 analysis, includes organic molecules complex enough that scientists are actively investigating whether some of them might be precursors to the building blocks of biology. But here's the problem that a study published in February of 2025 in Communications Earth and Environment placed directly in the center of this conversation. Even if life exists in Enceladus's ocean, we might not be able to detect it. The researchers, led by Flynn Ames at the University of Reading, modeled the physical dynamics of the ocean and found something deeply inconvenient. Enceladus's ocean forms distinct layers based on temperature and salinity gradients, the same layering that occurs in Earth's oceans, but potentially more pronounced given the specific conditions of a sealed ice-roofed body of water. These layers significantly slow the movement of material from the deep ocean floor, where hydrothermal vents would support any life that exists, up to the surface where the plumes form chemical signatures, organic molecules, and any biological material would need to transit through these layers before reaching the ice and being ejected into space. And as they transit, they degrade, they transform, they become unrecognizable. What reaches the plumes may bear almost no resemblance to what exists at the vent communities 3 or more kilometers below. The study's conclusion was sobering. Even if life is thriving in Enceladus's deep ocean, the signatures of that life might be invisible to any instrument in a spacecraft flying through the plumes. We might be sampling an inhabited ocean and reading it as empty simply because the ocean itself is hiding its own biology from us. And in November of 2025, new findings about Enceladus's heat flow added another dimension to this picture. Cassini data, reanalyzed with updated models, revealed that the moon releases heat from both its south pole, where the active geysers are located, and from its north pole, a discovery that had not been recognized before. This bilateral heat release suggests the subsurface ocean is being maintained by a more complex and more powerful internal heating system than previous models had accounted for. A warmer ocean, distributed more evenly, would potentially support biology over a larger area and at greater depths than a system driven by a single southern hotspot. Scientists studying these results noted that the balance of heat could allow the subsurface ocean to remain in a stable state for geological timescales, which is significant because life requires not just the right conditions but the right conditions for long enough that biology can emerge and persist. Move from Saturn to Jupiter. Europa is Jupiter's 4th largest moon and has been the target of intense scientific interest for decades. It is covered in a smooth, fractured ice shell beneath which radar observations, gravitational measurements, and magnetic field data all point to a liquid water ocean, potentially 100 kilometers deep, containing more liquid water than all of Earth's oceans combined. The presence of oxygen on Europa's surface, produced by radiation breaking apart water ice, provides a potential energy source for life if that oxygen can find its way through the ice into the ocean below. The chaotic terrain visible on Europa's surface, regions where the ice has been fractured and refrozen in complex patterns, suggests that material does exchange between the surface and the ocean, though the rate and mechanism of that exchange are still debated. NASA's Europa Clipper spacecraft, launched in October of 2024, is currently en route to Jupiter and will arrive in 2030. Its primary mission is to determine whether Europa's ocean is habitable, and it carries instruments specifically designed to search for chemical signatures of biology in any material that has migrated from the ocean to the surface or is currently being exchanged across the ice-ocean boundary. A cryobot concept, a probe that would melt its way through the ice and release autonomous submersibles to explore the ocean directly, is being developed and was field-tested in 2026 under Antarctic ice as a functional analog environment. Now go to Titan, Saturn's largest moon, a world so strange that it required multiple missions before scientists fully accepted what they were seeing. Titan has a dense nitrogen-rich atmosphere, thicker than Earth's, which gives it an orange haze visible from space. Beneath that haze, it rains. Not water, rain. Methane rain. Liquid methane fills lakes and seas across Titan's surface, in the same way water fills Earth's lakes and oceans. Rivers of liquid methane carve channels through a landscape of water, ice. The temperature is minus 179 degrees Celsius, far too cold for any chemistry we associate with life, but here is the specific possibility that makes Titan something more than a scientific curiosity. Theoretical chemists have proposed that in liquid methane, under Titan's conditions, a completely different kind of chemistry could work. Not the water-based carbon chemistry of Earth. Something using liquid methane as its solvent, with nitrogen-based molecules playing the structural roles that proteins and lipids play in Earth's biology. This chemistry has never been observed. It has never been proven to exist. But it has also never been proven to be impossible. NASA's Dragonfly mission, a rotorcraft lander, is scheduled to launch in 2028 and arrive at Titan in 2034, specifically designed to explore its surface and chemistry in detail. Titan is not a speculative target, it is a mission destination. And then there is 3IATLAS, discovered on July 1, 2025. This interstellar object, the third ever identified passing through our solar system after Oumuamua in 2017 and Borisov in 2019, arrived from outside the solar system on a trajectory that brought it through the inner solar system. Unlike Oumuamua, whose composition and behavior generated substantial controversy about whether it might be an artificial object, 3I Atlas has been characterized more conventionally by most of the scientific community as a natural interstellar body, but its passage through our solar system highlights something that is easy to overlook in discussions about alien life. The solar system is not a closed system. Material arrives from interstellar space continuously. Comets and asteroids brought organic molecules to Earth during the period of heavy bombardment 4 billion years ago. Interstellar objects are demonstrably capable of transiting through planetary systems. The panspermia hypothesis, that life or its precursors can travel between star systems on rocky material, is not ruled out by any current evidence. If life exists or existed around another star system, and if that life or its chemical precursors could survive the journey on an interstellar rock, the question of whether Earth, or any body in the outer solar system, might have received seeded material from elsewhere, is a question that 3IATLAS's existence makes harder to dismiss with a confident no. The Oort cloud adds a final layer to this. The Oort cloud is the vast spherical shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units from the Sun. It contains perhaps 1 trillion icy objects, most of which we have never observed directly because they are too distant and too small. These objects formed in the early solar system and were flung to the outer reaches by gravitational interactions with the giant planets. They have been sitting in the cold dark of the outer solar system for 4 billion years, and because the Sun's gravitational influence extends to the Oort cloud, but barely, these objects also sample the interstellar medium. They are, in a sense, at the boundary between our solar system and the space between stars. If any material from outside the solar system has been slowly accumulating in the outer reaches of our cosmic neighborhood over the past 4 billion years, the Oort cloud is where it would concentrate. What all of these locations share is a property that the history of life on Earth makes scientifically significant. Every one of them contains one or more of the 3 things that life requires: liquid water, energy, and chemistry.